Yes?
Yeah,
yes,
we saw
yeah,
that.
Okay,
it showed
great,
it.
thank you. Great, so thank you very much for inviting me today. I'll be talking about Lagrangian cobordisms and Lagrangian surgery. The general plan of attack will be first get through the introductory material. Then I want to talk a little bit about Lagrangian cobordisms and why they're an interesting object to study for symplectic geometers. Then I'll review some kind of known facts about Lagrangian surgery and how we can visualize them. So that part should be full of a lot of pictures. And then we'll get to the main theorem, which is showing that every Lagrangian cobordism can be decomposed into Lagrangian surgeries. And then finally, at the end, time permitting, I want to talk about some applications and some speculations about Lagrangian cobordisms. Before talking about Lagrangian cobordisms and Lagrangian surgeries, I just want to talk about surgery of manifolds and cobordisms of manifolds. So here's the notation that I'm going to be using for this talk. So two manifolds, which I'll call M cross P and M cross P, are related by P surgery if there exists another manifold whose boundary is a SP cross Sn minus P minus 1, from which you can obtain the original two manifolds by either gluing in an SP cross Dn minus P, or you can glue in a dP plus 1 cross Sn minus P minus 1. So I know that this notation over here with this cross and uncross is not the usual notation for talking about surgery of manifolds, but it'll become very important when we talk about Lagrangian surgery later. One of the key features about surgery of manifolds is that when you have two manifolds which are related to each other by surgery, there exists a cobordism between them, called the trace cobordism of the surgery. One kind of interesting feature about trace cobordisms is that if you take the trace cobordism for a P surgery, that's the reverse cobordism of a trace cobordism for N minus P minus 1 surgery. So that's a statement that says that every surgery gives you a cobordism. And there's a theorem that says the opposite thing is true also for manifolds. So every cobordism N can be decomposed into cobordisms of the form of trace cobordisms. So maybe the picture for this is that if you take a cobordism that looks like this, then you can take the cobordism and slice it down the middle. And then the first half of this is going to be the trace cobordism for one surgery. And the second half of this is going to be the trace cobordism for 0 surgery. And this is a great theorem. It means that if we want to prove things about cobordisms, we could prove them instead by proving them for concatenation and proving them for compositions of cobordisms. For trace cobordisms. What we're going to do to this talk is we're going to take these theorems and we're going to insert the word Lagrangian everywhere. So that requires some explanation. So there's a notion of surgery on Lagrangian submanifolds, which come roughly from two different sources. The first one is Lagrangian connect sum, which was introduced by Polterovich. And this takes two Lagrangians, L0 and L1, which intersect transversely at a point X, and produces from it a Lagrangian called the connect sum of L0 and L1 at X. The operation which is done is you take a neighborhood of this self-intersection, or of this intersection, you replace it with a neck. This is some kind of explicitly parameterized thing. Then in 2015, Louis Haug, based on some inspiration from work on Legendrian surgery, introduced a whole slew of operations called P antisurgeries. And this takes as input some Lagrangian L, which has an anti-surgery disk. So this is an isotropic disk whose boundary is an L. And then with this data, he produces a Lagrangian submanifold, the anti-surgery of L along this disk, which has one more self-intersection than the previous Lagrangian had. So this gives us kind of a model for how we want to take a Lagrangian submanifold and modify it by surgery. The second part of the story are Lagrangian cobordisms. So a Lagrangian cobordism is the following piece of data. A Lagrangian cobordism between L minus and L plus, which are two Lagrangian submanifolds X, is a Lagrangian submanifold in one dimension higher. So I guess one complex dimension higher. So it's a Lagrangian in X cross C, whose ends look like L minus cross the negative real ray and L plus cross the positive real ray. Over here, I need to look like my Lagrangian L minus in the fiber, but then I'm allowed to do whatever I want. And then I have to look like a line in the base. Over the middle, I'm allowed to do kind of whatever I want. And I see that there is something in the chat. In what sense in anti-surgery is a new operation? Right, so the anti-surgery operation, here I showed that it is in fact just the opposite of doing Polterovich surgery, but this is an isotropic disk. So as I put in different disks over here, we will get different types of anti-surgeries. Not all of them are the same as running Polterovich backwards. And in fact, later in this talk, I'll describe kind of what is the higher dimensional analogs of Polterovich surgery, for which anti-surgery is the new surgery run backwards. Does that answer your question? To get the reverse of Polterovich surgery, you use a Lagrangian disk. And if you wanted to get, and if you use an isotropic disk, you'll get something which isn't Polterovich surgery run backwards.
Thanks. That's exactly what I meant. Yes.
Okay, great. So, right, so these Lagrangian cobordisms are Lagrangians which exist kind of in one complex dimension higher. Right, so the theorem that we'll talk about today is a decomposition theorem, which says that every Lagrangian cobordism K can be decomposed as the composition of either anti-surgery or surgery trace cobordisms. So this is just a tad bit different than the theorem for manifolds that said that you could be the composition of surgery trace cobordisms. Here, there's a difference between anti-surgery and surgery, but apart from that, it looks very similar to the theorem that you have for manifolds. So before we get into talking about the proof of this theorem, I want to motivate why we would want to study Lagrangian cobordisms. And this motivation will also give us some examples to work on, which will give us intuition for the proof. So why do we use Lagrangian cobordisms? Well, there's some existing work of Biran and Cornea, and also some other work of Nadler and Tanaka, which say that Lagrangian cobordism gives us a really geometric intuition for understanding algebraic relations between Lagrangian submanifolds. And here I mean algebraic relations in the Fukaya category of X. I'll just give kind of the short version of the theorems that they have. One specialization of their theorem says that if you have a monotone Lagrangian cobordism with two ends, so one that goes from L plus to L minus, then there's an exact sequence in the Fukaya category which says that L plus and L minus are equivalent. So searching for these monotone Lagrangian cobordisms is proving some kind of equivalence. Oh, there's some weird feedback with my microphone. That's unfortunate. Does this sound a little bit better? Great, thank you. For some reason, I only have this problem with Zoom. I've had it before, so I'm not sure exactly what's going on. But please let me know if the feedback starts again. All I need to do is just yeah, I just need to kind of restart the microphone and then it resets the noise cancellation software. So if I have a monotone Lagrangian cobordism with two ends, I get an equivalence of objects in the Fukaya category. A different specialization of this theorem says that if you have a monotone Lagrangian cobordism with three ends, then you get an exact triangle in the Fukaya category. And the generalization of this says that if you have a monotone Lagrangian cobordism with k ends, you get some kind of iterated exact triangle between your Lagrangian submanifolds. So this result in particular kind of seems very powerful, that whenever you have a monotone Lagrangian cobordism, you get an equivalence. However, I'd like to point out that we actually do not know of any two-ended monotone Lagrangian embedded cobordisms, other than variations of L cross R inside of X times C. So it would be, this is a theorem which is waiting for examples to be thrown at it. Unfortunately, we just don't right now yet have the geometric intuition to construct kind of any interesting monotone two-ended embedded Lagrangian cobordisms. And there's some indication that this is actually kind of a fairly tricky problem. So for instance, if we had a non-trivial example of such a cobordism, then we would settle the narrow-wide problem, which asks, are there monotone Lagrangian submanifolds whose Floer theory is non-zero and different from their Morse homology? So if you had a monotone Lagrangian cobordism, which has some kind of non-trivial topology, then the Floer theory of this would have to be equal to the Floer homology of its left end, or the Floer homology of its right end. But the Morse homology would certainly not be equal to the Morse homology of either end. So finding one of these examples would be very exciting. So let's talk about the examples of Lagrangian cobordisms that we do know exist. The first example, which we're going to be using quite often in this talk, is called the suspension of a Hamiltonian isotopy. So let's start with an exact Lagrangian isotopy inside of X. And what do I mean by an exact Lagrangian isotopy? I mean that if you take the flow of this isotopy, pair it against a symplectic form, and pull it back to your Lagrangian, that's an exact form. And in fact, I want to give it a primitive, which I'll call HT, which I'll frequently call to as like the generating Hamiltonian for the isotopy. Hiro Tanaka asks, for cotangent bundles, finding such cobordisms would also be very close to a counterexample for the Arnold conjecture. Sorry, for the nearby Lagrangian conjecture. Yes. Yes. Right. So I think, yeah, finding an example in a cotangent bundle would be very exciting, but even just finding any example in any symplectic manifold would be kind of an interesting thing already. Right. So kind of the simplest examples of Lagrangian cobordisms that we know are these exact Lagrangian isotopies, and they're just explicitly parameterized for us. You take L cross R and you map it to X cross C by in the first coordinate, mapping it to the time t position of the isotopy, and in the C coordinate, well, the real part seems to track the parameter of the isotopy, and then there's kind of an additional factor which shows up, and that's just required to make it Lagrangian. So these suspension cobordisms not only remember the isotopy, but they remember the primitive that you chose for the isotopy. The second example of Lagrangian cobordisms, which are very prevalent, are related to Lagrangian connect sum. Why? Why is this a Lagrangian? I don't have a really good intuition for why it's a Lagrangian besides you compute it in coordinates.
No, sorry, I'm meaning why it is so close to providing a counterexample for nearby Lagrangian conjecture.
Right, so I suppose if you had so if you had a non-trivial example inside of x cross C, then you could think of this as maybe x was equal to t star m. Now this is equal to t star m cross r. Now you have kind of a very interesting Lagrangian inside of t star m cross r, which presumably is isomorphic as an object of the Fukaya category to the left side, but not to the right. Higher hope to be heard in that. Okay. All right, maybe we should discuss this.
We'll discuss this later.
Yeah. Great. Right. So another kind of bread and butter Lagrangian cobordism is a connect sum cobordism, and it just says that if you have Lagrangian manifolds L0 and L1 which intersect transversely, then there's a three-ended Lagrangian cobordism between L0, L1, and their connect sum. From before, we said that whenever we have a three-ended Lagrangian cobordism, this gives us an exact triangle. So you should think of this as kind of being some other version of the surgery triangle given by Fukaya, Ohta, Ono in their work on Lagrangian connect sum. Finally, there's one other kind of interesting example that I would like to think about. Great. Renato asks, is there necessarily a local system for L plus for which each of L plus is equal to minus and distortion is that?
Jeff, can you restart your microphone?
Is that a bit clearer now?
Yes, that's much better.
I'm so sorry about this.
It's all right. Did you see the question from Renato?
Yes. So it asks if you have a local system in L minus for which h of L minus is not equal to 0, is there necessarily a local system in L plus for which the Floer theory of L plus is not equal to the Floer? So which the Floer theory of L plus is equal to L minus. I believe so. I think in Biran and Cornea's work, there's it should work with local systems. In particular, I think if you look at a paper by Louis Haug on cobordisms for the torus, he outlines the steps that you would need to take to make this result carry over for local systems as well. Great. So there's one other example that I want to give, which is one other example which I want to give, which is Lagrangian cobordisms coming from Lagrangian correspondences. Lagrangian correspondence is a Lagrangian inside of x1 cross x2, where I equip it with a symplectic form so that I put the negative symplectic form on the first factor and the regular symplectic form on the second factor. And a nice feature about Lagrangian correspondences is that they can be composed. So given two Lagrangian correspondences, one from x1 to x2 and one from x2 to x3, then I can compose them by taking a fiber product over the common x2 factor. Now, this will only give me immersed Lagrangian submanifold if L12 and L23 have some kind of transversality property, but you could hope to achieve this transversality property by applying some type of perturbation, say a Hamiltonian one. Then a question becomes, is this construction independent of the choice of perturbation that you use to achieve transversality? And the answer is no. You could take two different perturbations of your correspondences and get kind of two very different geometric compositions out. However, if L12 and L12 prime are Lagrangian cobordant, then their compositions with a third Lagrangian, L23, are also Lagrangian cobordant. So correspondences preserve cobordism type. So in particular, if you took two different Hamiltonian perturbations to achieve transversality, then L12 and L12 prime are cobordant using the suspension cobordism, and therefore these compositions are Lagrangian cobordant as well. And if everything turns out to be monotone, then they have the same Floer theory. So this kind of shows that Lagrangian cobordism class is probably the right class of equivalence that you want to be thinking about the Lagrangians with. Okay, so maybe that's some motivation for why we like working with Lagrangian cobordisms. Maybe before I move on to talking about Lagrangian surgeries, I'll pause to see if there are any questions. Okay, moving on to Lagrangian surgery. So before we get to Lagrangian surgery, there's a particular Lagrangian that I want to talk about, which is the Whitney sphere. The reason that I want to talk about the Whitney sphere is that if you were trying to teach someone about surgery, the first thing that you would teach them about is how to fill a sphere, right? Every surgery is completed by filling in a sphere, essentially. And so what we should first look for are Lagrangian submanifolds, which are null cobordant. And the Whitney sphere is an example of one of these. So the Whitney sphere is a Lagrangian sphere, which has this kind of very explicit parameterization. And the thing that you notice about this parameterization is that this gives us a sphere that has one self-intersection. So this self-intersection occurs when the x0 coordinate is either equal to 1, or sorry, when the x0 coordinate is equal to r, or the x0 coordinate is equal to -r. This is a sphere with this parameterization has a radius, and you can create a cobordism by altering that radius and bringing that radius to 0. So that's an operation that will take this Whitney sphere and shrink it down to 0 size. So let me just kind of draw a sketch for what happens as I try to decrease this radius. So let me describe the exact isotopy for the Whitney sphere. So the Whitney sphere will be mapped to this figure 8 in the plane, or the sphere is mapped to the figure 8 in the plane in such a way that the maximum of the sphere and the minimum of the sphere under projection to the z0 coordinate is mapped to the same point here of the origin. And if I just take the exact isotopy, which is generated by this Hamiltonian, you see that this exact isotopy flows the Lagrangian in an inward direction. So after applying a little bit of the flow, my Whitney sphere becomes smaller, and if I kind of cleverly control the rate of this flow, it eventually disappears. So this is the first type of surgery that we could consider, which is what is the surgery which takes a sphere and removes it. Our main idea for constructing our surgeries is going to be very similar to an idea which shows up in a paper of Louis Haug called Whitney degeneration. And the strategy that we're going to have is we're going to identify a Whitney isotropic sphere inside of our Lagrangians with some kind of appropriate normal bundle. And then we're going to replace that Whitney isotropic with the null cobordism for the Whitney isotropic, where the cobordism parameter it moves in the direction of the normal bundle. So I think this is probably easiest done by pictures as opposed to writing it out in coordinates, for at least at first. So I'm now going to give a slightly overcomplicated description of how to resolve a self-intersection using this viewpoint. So here I have a Lagrangian of dimension 1. It has a self-intersection. And essentially what we're going to do is we're going to look at this self-intersection point over here and think to ourselves, that's an S0, right? There's 2 points there. That's Whitney's zero sphere. And then I have some normal direction U, and in every slice of this normal direction, I see a Whitney zero sphere. So this is like a one-dimensional family of Whitney zero spheres. And the way that I want to do the surgery is I want to take that Whitney zero sphere, cross an interval, and replace it with the null cobordism for the Whitney zero sphere. Oh, I have not been catching up on the chat, but it looks like there are not any questions in the chat. So
Do you want to pause for questions, see if anyone wants to ask you anything?
Sure, I'll pause for a question now, but for discussions about...
I think we're agreeing. We're all in agreement.
Okay, you're all in agreement. Okay, great. Okay, so this is how you would construct the Polterovich connect sum in kind of some very complicated way. So that's kind of an easier example. Let's try something a little bit more difficult. So let's try looking at a zero handle in dimension 2. So I'm going to draw some Lagrangians inside of T star R2. And the way that I'm going to draw these Lagrangians is that I'm going to represent them as sections of the cotangent bundle, and I'll represent those sections as vector fields. So here's one Lagrangian, L1. It's the graph of x1 squared plus x2 squared. Here's another Lagrangian drawn on top of it, the graph of minus x1 squared minus x2 squared. And these are two Lagrangian submanifolds. They intersect here at the origin. Let me maybe do that in green. And they intersect at 2 points in the origin. So at the origin over here, I see a Whitney S0. So I see Whitney S0, and I have a whole R2 family of them. So this is exactly the situation where I expect to be able to apply this type of surgery. And the way that we apply the surgery is we take one of these S0s, and in the R2 direction, we put the null cobordism for the S0. So this is at most points two shaded cover of the plane. Over here in the center, I've kind of put a hole. And this is describing for me some Lagrangian submanifold, which is actually exactly the same as the Polterovich connection. So these are some warm-up pictures for the example that I really want to get to, which is a one handle in dimension 2. So again, I'm going to draw this as some section of the cotangent bundle of R2. So I don't actually have a precisely written down primitive for this vector field, but it looks like it has index 1 critical point over here in the center, and then it kind of flows out to the side and drops off to 0 size on the side. So if I take this red vector field and this blue vector field, which is exactly the same vector field just with a minus sign attached, this gives me some Lagrangian submanifold inside of T star R2. And this Lagrangian submanifold has exactly one self-intersection over here in the center, where both of those gradient vector fields are 0. Now, one thing that you could do at this point is you could just say, well, I see a self-intersection. What I'll do is I'll apply Polterovich exact surgery, and that will give you some different submanifold. However, if you cut along this slice over here, you'll see an isotropic sphere with a self-intersection. So this is a Whitney isotropic S1. In a one-dimensional family. And so what I want to do is I want to take the edge of this, kind of cut out everything in the middle, and replace these sections over here with the null cobordism for the Whitney S1. And if you do that, you'll get this Lagrangian over here on the right side. So notice that it matches the previous example at the boundary, but I've removed the area where I previously had a Whitney S1.
Sorry, Jeff, I'm confused. So if I look near the intersection, I don't understand the difference between the two pictures. It's just two transverse Lagrangians meeting.
Right.
So you're now doing some procedure that is not just local to the intersection of just the of two Lagrangians?
Exactly. It's not local to the intersection of two Lagrangians. You have to go and search further until you find an entire isotropic sphere.
So the point is that there is one originally how many intersection points are there between these two things?
There's only one intersection point.
Okay, but so when you say you find this S1,
so one point of confusion, it seems. So the red vector field and the blue vector field are two different charts which parameterize one Lagrangian. So there's only one Lagrangian here, L, which is equal to the red chart, the blue chart union the red chart.
Okay.
So inside of this one Lagrangian L, I find an isotropic sphere which has a self-intersection.
I think I understand now. Thank you.
And then what I want to do is I want to take that isotropic sphere with a self-intersection and pinch it down until it disappears. And then kind of be a little bit clever about how I insert some filling for the thing I pinched off.
I think Oleg has a question which maybe you want to confirm.
So just to make it I understand, you have two Lagrangians intersecting at a point, and I pick a Whitney sphere in any dimension contained in these two Lagrangians. Almost. I have one Lagrangian which has a self-intersection, and then I pick a Whitney sphere that contains this self-intersection. Great. Right. I think maybe at this point it's a good idea to bring out just what this neighborhood really looks like. The data that we're going to need is the following, which is a Lagrangian immersion, and a p-surgery configuration. So a p-surgery configuration is the data of a manifold U with boundary of dimension n minus p, a symplectic embedding of T star dp cross T star U into X, and a smooth function which depends only on the collar parameter of the boundary, is supported only in the collar and is equal to the collar coordinate at the boundary. And all of this data is chosen in such a way that in this neighborhood, T star dp cross T star U, I can parameterize my original Lagrangian immersion as a collection of Whitney spheres over the parameter U. So in specific coordinates, it's a little bit hard to read out, but these coordinates over here look like the coordinates parameterizing a Whitney sphere from our original parameterization of a Whitney sphere. And this R coordinate over here is controlling the radius of the Whitney sphere. So this is this is describing a certain type of neighborhood where you see a certain family of Whitney spheres. And this is the type of thing that we're going to be able to search or often replace. I think I'll skip that slide. The proposition is that starting with a surgery neighborhood, we can construct another Lagrangian submanifold, which topologically differs from my original submanifold by surgery. And additionally, there is a Lagrangian trace cobordism between my original submanifold and my surgered one. And let me just draw how we construct this Lagrangian trace cobordism. So for example, if I wanted to construct the Lagrangian trace cobordism between L0 disjoint union L1 and the surgery, the Polterovich surgery at a point X, then the way that I would construct this trace cobordism is inside of X cross C, I would take L0 cross some path gamma 0, L1 cross some path gamma 1. And these two Lagrangians inside of X cross C intersect each other over a region L0 intersect L1 cross array.
Jeff, you have a question from Oleg.
Great. And the question from Oleg is, if the Lagrangian immersion is strongly exact, is the result of your surgery also exact? I don't know. I haven't looked into that, but that's a good question. Right. So the point being is that L0 cross gamma 0 and L1 cross gamma 1 intersect over what now appears to be a Whitney sphere cross R. And so I can apply the surgery construction to this to construct the trace cobordism. So once I apply the surgery construction to this configuration, I'll get a surgery trace cobordism between L1, L0, and L0 connect sum X, L1. Now, there's a key difference to surgery of manifolds for Lagrangian surgeries, which is that the trace of a p surgery is not the trace cobordism of a P surgery is not the same thing as reversing the trace cobordism of a N minus P minus 1 surgery. One of these has a left end which is immersed and a right end which is not immersed, and the other one has a right end which is immersed and a left end which is not immersed. So there really is a difference between surgery and anti-surgery, as opposed to when you look at surgery of manifolds, where you could represent every surgery cobordism by the trace of the surgery of opposite degree. So we'll call the first type of cobordism a Lagrangian surgery trace cobordism, and the second type of cobordism a Lagrangian anti-surgery trace. So now we have a whole bunch of different surgery operations and a whole bunch of different cobordisms. And the question is this enough to obtain all of the Lagrangian cobordisms? And here I'm going to give a sketch of the proof. So the first thing that I need to define is the slice of a Lagrangian cobordism. So given a Lagrangian cobordism, you can obtain a Lagrangian in the X parameter by taking your Lagrangian cobordism, taking some real line, looking at everything which lives above that real line, and projecting it to X. So you can look over the parameter of your cobordism, kind of find some time that you like, slice it there, and obtain a Lagrangian in X. So some particularly nice slices is that if I slice at the left end of the cobordism, I get L minus, and if I slice at the right end of the cobordism, I get L plus. And this is defined provided that the intersection is transverse. So for regular values of the projection from the cobordism to R, the slice is an immersed Lagrangian submanifold of X. Additionally, if we go between two values of the T parameter, which contain no critical values of the projection to the T parameter, then the slices are exactly isotopic. Furthermore, projection to the imaginary coordinate, which I'll call HT from now on, is a primitive for this isotopy. So this is just saying that if you have a Lagrangian cobordism and all of the slices are isotopic to each other, sorry, if you have a bunch of slices and you don't encounter any critical points as you take these slices, then you have an exact Lagrangian isotopy, and the isotopy that you see, or the cobordism that you see, is exactly the suspension cobordism that we constructed earlier. So for understanding the structure of Lagrangian cobordism, you only really need to understand what happens at the critical values of pi r. So the first fact that we need is that we can make sense of this. So it's a fact that there exists a Hamiltonian isotopy, so that you can take a Lagrangian cobordism and put it into a general position so that projection to the real coordinate is a Morse function. So the critical points of this will be separated, and you really can't get some kind of decomposition. So maybe an example to look at over here is if you look at S1 inside of C, and you look at S1 cross gamma, if you look at S1 cross gamma, a Lagrangian cobordism inside of C cross C, then this is an example of a cobordism where projection to the real coordinate is not Morse. In particular, if I look at the slices of this, over here, the slice appears to be kind of two circles exactly on top of each other. And then there's only one other kind of interesting other slice, which is over here, where the slice is empty. However, after applying some type of Hamiltonian perturbation, this cap-shaped Lagrangian can be kind of smeared out on the right end. And my slices will come in three different fluids. Oh, thank you.
Can you restart your audio?
Okay, are we better again?
Yes, much better. Thank you.
Great. I am so sorry.
That's all right.
Right. So we now have three different kinds of slices. So this slice looks the same. It's roughly two circles stacked up on top of each other. The slice on the right is again empty, but now there's an interesting intermediate slice, which is a figure 8, which is obtained by these two circles stacked up on top of each other and applying surgery to one of the self-intersection points. Right, and now in this picture, you can see that between this slice and this slice, I've applied a zero surgery, and between this slice and this slice, I've taken a Whitney sphere and I've knocked it off. So this provides some kind of good evidence that after we apply Morse homotopy, after we apply a Hamiltonian isotopy, we should be in the place where we can decompose our Lagrangian. So in this talk, I'll give a statement which is slightly weaker than the main theorem, which is to say that after you apply a Hamiltonian isotopy to your cobordism, at every critical value of this projection to the real coordinate, either the slices before the critical points have a self-intersection, or the slices after the critical points have a self-intersection. This means that if you have some kind of Lagrangian cobordism, one end of the cobordism is more immersed than the other one is. More embedded than the other one is. And once you find these self-intersections, it's relatively easy to find the Whitney spheres which contain these self-intersections. The proof is based on a first observation, which is that a point in your cobordism cannot be both a critical point of projection to the real coordinate and projection to the imaginary coordinate. If it was, then the tangent space of the Lagrangian cobordism would be completely contained in the fiber, but then it couldn't be Lagrangian. So for simplicity, I'll assume that I have a critical point whose value under the real projection is 0. And near this critical point of pi r, there's 3 different types of scenarios which can occur. So over here, I've drawn the level sets of projection to the real factor. So these level sets are the slices of k restricted to t. So this is some neighborhood in k of x. Now, what I'm going to do is I'm going to superimpose on top of this the level sets of h. So The first scenario is that the level sets of H have a gradient which points in the negative direction of the level sets of R. The second scenario is that the level sets of H have a gradient which point in kind of the positive cone of the projection of R. And the third scenario is that the level sets of H are somehow tangent to the level sets of R at 0. Now, this case is bad, but you can remove it after applying another Hamiltonian isotopy. So let's assume that we're in this first case where you have that the level sets of H have normal direction which points in the positive direction, points in the negative direction of projection to the real coordinate. So if you're in that case, every slice which has negative value will have 2 critical points of HT. So I can kind of draw them for you over here. This is just the place where the level set of HT is parallel to the level set of pi r. Right, so I guess here we're using like the method of Lagrange multipliers or something. And we know that the critical points of HT are tending towards this point X. Secondly, we know that this HT is the primitive defining the Lagrangian isotopies of the slices K restricted to T. The last piece of data is that nearby the critical point of HT, there's a fixed point of the isotopy KT. So what you have is a sequence of points which are nearly fixed by the isotopy, and they are all tending to the same point over here. In particular, this means that in a neighborhood of here, there's a point which matches something in the neighborhood of there. So we conclude that the slices KT with t less than 0 will have a self-intersection. And similarly, if we were in the case where the level sets of H were pointing in the positive direction of projection to the real coordinate.
Jeff, can you restart your audio again?
I am again so sorry about the audio situation. I think this is the longest Zoom call that I've given, and I didn't realize that it would kick in this many times.
That's okay.
So we can conclude that either the positive slices or the negative slices will have a self-intersection point. And from this self-intersection point, you can go and find yourself a Whitney-immersed sphere. I guess before I get to applications and speculations, are there any questions? Okay. Okay, so what happens now that we know that a Lagrangian cobordism can be broken up into the composition of surgery traces and anti-surgery traces? Well, an upshot is that you can prove things about Lagrangian cobordisms by construction. So you prove it for trace cobordisms and anti-surgery trace cobordisms and then you prove that the property holds under composition, and then you're good. Maybe a downside is that the world of Lagrangian cobordisms is perhaps a little more tame than we would have hoped for. So these are the only Lagrangian cobordisms that you can build, so you're not going to find anything truly exotic inside of this world. So let's kind of see what this says about the about two-ended Lagrangian cobordism. So this was the question that we were bringing up earlier. Can we find a two-ended monotone Lagrangian cobordism? This result says that there's something actually kind of very special that happens when you look at a two-ended monotone Lagrangian cobordism. So the Floer homology of the cobordism is supposed to match the Floer homology of the left end. And the Floer homology of the cobordism is supposed to be a deformation of its Morse homology. Now I can describe the Morse homology of K from handle attachments to the left end. And every time I do a handle attachment, I'm going to be modifying the Morse homology of the cobordism, so it kind of drifts further and further away from matching the homology of the left end. However, since the Floer homology is supposed to match, it means that every time I do a handle attachment, this has to be exactly canceled out by the presence of some holomorphic disk. So let's see this in action now that we know that our Lagrangians. Am I sounding clear again?
Yes.
Great. So the example that I want to look at is just the surgery trace cobordism between two Lagrangians which intersect transversely and their connect sum. And now I will apply an isotopy to this surgery to introduce two self-intersections. Now, let's say that this self-intersection occurs at a point X. Then, over this region over here is a holomorphic teardrop, which you can exactly just parameterize by X comma Z, where Z is in C, and this entire cobordism is living inside of X cross C. So what's the thing that we notice? Well, as we travel along our Lagrangian cobordism, sure, it looks like we're picking up some new generator of Morse homology from the surgery, but because of this result on the decomposition, we know that at the same time we pick up a self-intersection. And on top of this, we can find a holomorphic teardrop which goes through the downward flow space of the surgery handle and winds up on the self-intersection. Now, a kind of speculative proposal would be that this would give you a method for computing the Pauli complex of the trace cobordism from the left end. So the Morse function of the left end will have two more generators than the Morse homology of the right end, but the right end will have two more generators from self-intersections in the left end. And counting teardrops would give a bijection on the level of chains. Now, that can't always be the case. And maybe let me give an example of where you can't construct a continuation map from this data. So there's a Lagrangian cobordism between the following two Lagrangians, which are obtained from taking matching paths in Lefschetz vibrations. So this Lagrangian S2 over here and this Lagrangian S2 over here are Lagrangian cobordant, but they're not equivalent in the Fukaya category, no matter what local systems you equip them with. This technique of proof would allow you to compute the Floer cohomology for that Lagrangian cobordism, but then it would also allow you to show that Lagrangian cobordism doesn't provide a continuation map in the Fukaya category because it's obstructed. I think I'm out of time, so I will stop there. And thank you everyone for showing up.
Great. Let's thank Jeff for the great talk. So before we take questions, I'd just like to post a couple of links in the chat. The first link is any suggestions for future speakers. And the second link is any feedback you have about our seminar. Okay, so are there any questions for Jeff?
Can you go back to the penultimate slide, the one you skipped? Thanks. Can you tell us what was supposed to be on the slide?
Thank you. I muted myself to avoid creating terrible sounds, but it also prevents me from talking. There's a Lagrangian cobordism between the Chekanov and the product type tori and the complement of a conic in C2. So between this torus and this torus, there's a Lagrangian cobordism. And that Lagrangian cobordism is unobstructable by a bounding cochain. And the way that you find this bounding, am I still muted? Oh, no. So the way that you find this bounding cochain is essentially by, you can construct this bounding cochain by breaking this cobordism up into surgeries and then carefully keeping track of which holomorphic teardrops you see in that surgery. And if you kind of take this cobordism and this bounding cochain and you restrict the bounding cochains to the left end, then you find that the Chekanov type torus equipped with this bounding cochain is equivalent to the product type torus equipped with this bounding cochain. Now, the bounding cochain is somehow very important because if I was to remove this bounding cochain, then I wouldn't be able to find an equivalence between those two objects. And then the question is how are those bounding cochains related to each other? In a work which I worked on last year, I showed that the relationship between those two bounding cochains is given by a wall crossing, or it matches the wall crossing transformation known for local systems between the Chekanov and product type torus. However, the computation is really just that. It's just I computed what the bounding cochains were and I showed they match some wall crossing transformation. It would be interesting to see kind of why that generally should be the case, not just for Lagrangian cobordisms like this, but for, in theory, any Lagrangian cobordism now that we know the decomposition theorem. I think the PDF is listed in a slide, in a link, which is at the very top of this talk. I'll post it. Catherine has just posted it one more time. After this talk, I'll send Catherine the marked up version of these slides because I know that I added a couple of pictures on the way.
So if I can make a comment, Jeff, one potential application of what your decomposition is through is to measure distances between Lagrangians and to see how the how they fit into a metric space. Because cobordisms are having shadows, and you can measure them. And it's kind of an interesting game because you're seeing here objects that are quite different in your case. And a second comment is that there is maybe related to you, but a slightly different way to look at decomposing cobordism into surgeries, and also with a lot of pictures. So we have a paper with Paul called the Lagrangian Pictionary, which you can see exactly the picture you have in front of you right now.
Yes, I was guessing this was the one.
There are more, but just to say it's a different way, but it's not as geometric as yours. Because what you do is a very geometric decomposition, and our decomposition is through a sort of a triangulated category, which is purely geometric, but it's kind of, each cobord is sort of equivalent in a certain sense to a surgery, but it's not written as an iterated sort of construction of some sort.
Right. So my kind of take on this is that this decomposition result should provide a bridge between this FO cubed exact sequence and the mapping triangle which you have in your paper.
Yeah, I mean, I would say that relation is basically well understood if you understand really well the moduli spaces holomorphic curves before and after surgery. But okay, that right. In any case,
so Mohammed asks, do I have a categorical interpretation of the antisurgery for isotropic spheres? I do not, but it's something that is kind of a natural thing to think about next. Ideally, what you would want to understand is, I guess, in this slide over here, what is exactly the continuation map that you're getting from the left-hand side to the right-hand side by explicitly counting that holomorphic teardrop. And Marco asks, what happens if one replaces C with a general punctured curve? Great. In fact, even more interesting than maybe replacing C with a almost punctured curve, you could ask what happens when you replace C, when you place this entire setup with kind of the structure of a Lefschetz vibration. And these local models still kind of work, at least if you have Lefschetz vibration over C, where you get, as long as you have this kind of projection to the real coordinate. When you work over a general punctured curve, this would tell you kind of a local model for every portion of your Lagrangian, but I don't know if you would have this kind of decomposition into slices. You can imagine something going between the two punctures in some kind of interesting way. Did that answer your question, Marco?
Thank you. Yes, okay. Thank you. Sorry, I was thinking and I got stuck.
No worries. Hiro asks if the teardrops are certain holomorphic sections or more abstract disk maps. Can you give some indication of how to count these in practice? So they are a specific holomorphic sections. So they're disks with one output, which are constructed as holomorphic sections of X cross C. I have not done a computation to count them in practice, but my guess would be is that they're rigid. When you try, so the configuration of starting at this force point taking a flow line, going to the holomorphic teardrop, and outputting at the newly introduced surgery point should be a rigid configuration. That would be my guess, but I haven't checked it. Yes, definitely. There's a lot of care that needs to be taken for teardrops. These teardrops do have the advantage that, I mean, we really can honestly parameterize them. But I agree that if you wanted to make sense of this in some sense of saying that this is providing some kind of equivalence in objects in the Fukaya category, that would definitely require some kind of setup for the Fukaya category, which is comfortable handling teardrops.
So you have a question from Mohammed about, or a comment about the narrow-wide dichotomy, and then a question from Oleg.
Well,
Great.
I suggested that my comment can wait for after the question, for after the official record. But
Great. So yeah, so maybe I'll answer Oleg's question first. There's a notion of regularity of exact Lagrangian cobordisms and Weinstein cobordisms. This is a slightly different setting, but can you say anything about the regularity of these Lagrangians? Yes. So I haven't checked this for all surgery types yet, but if you take this surgery neighborhood, and at least I know for zero surgery, if you take this type of surgery neighborhood, and you need some additional condition on T star U. So I think that the Louisville flow on X needs to match that of T star U. Then the surgery cobordism that you get, the trace cobordism, should be regular. But I haven't checked for higher surgery configurations yet. Right, so I think like a particular example of this is in this surgery over here, where you're taking L0 cross gamma 0 and L1 cross gamma 1, and you surger them. This overlap region is non-compact, but it's non-compact just kind of in a trivial way off to infinity. So when you apply your surgery, you're going to still remain regular.
All right, well, this seems like a natural stopping point. So why don't we thank Jeff again, and then we can go into the discussion session. Thanks so much.
Thank you.